Uh, Good afternoon, everyone. And I want to welcome you to my lecture today. Today, we are actually starting a new chapter. This is chapter 8 on the sampling distribution. Okay, I want to say what we want to do today is very, very interesting. Okay, and what we want to do today actually justify our efforts in statistics. So the outline today, you're actually going to learn how to use central limit theorem to identify characteristics of a sampling distribution. Okay, now let's get started. For you to be able to understand what we want to do, I will actually, want to review the background. I want to tell you this. The appearance of reality is independent of human knowledge. I'm going to say that again. The appearance of reality, the appearance of the physical world is independent of human knowledge. And you know what? We actually want to take decisions that we don't want to regret under this environment. And that actually requires that we should have the understanding of our environment. We actually want to take decision in medical environment. We want to take a decision in physical environment, in economic environment, in psychological environment, in political environment, even in social environments. If we want to take a decision that we're not going to regret, then that requires our understanding of the environment. But I want to tell you this. We live in a stochastic world. We live in a probabilistic world. And if I really want to understand my environment, what I need to do is to go back to the population. I'm going to say that again. If I want to understand my environment, then we need to go back to the population. But let me tell you this. What am I looking for? Why do I need to go to the population? I'm actually looking for parameter. What do I mean by parameter? Parameter is an unknown population characteristic value. Look at that, unknown population characteristic value. I'm going to give you an example. The parameter could be mean, like I want to know the average annual income in the United States, also income in the United States. I want to know the numbers of female in US Congress. Or I actually, want to know the numbers of females in the Canadian Parliament. Or I simply want to know how many Americans approve the job the president is doing. That's a parameter. And that is why we call it unknown population characteristic value. But you know what? Study the entire population. It's actually going to be time consuming. And you know what? In terms of cost, it's not going to be cost friendly. And that is the reason why instead of us to study the entire population, we actually end up taking sample. What do we mean by sample? Sample is a fractional part of a population. We can also call it a subset of the population. But the sample has to be chosen in a way that every item in the population has equal chance of being chosen. Of course, we have different type of sampling scheme. But whatever sampling scheme we're using, The sample we choose at the end of the day should be a very good representative of the population. Now, if I go back to the example that I cited, that I actually want to know, what is the proportion of Americans that actually approve the job the president is doing? Of course, in that situation, my parameter is actually proportion. We could have situation where parameter is actually going to be average, and we also have situation where it's going to be proportion. Okay, but you know what? I don't need to investigate all Americans before I will be able to take a decision. I can take a sample, just like the one conducted recently by MSBC about, the percentage of Americans who approve the job the current president is doing. Now, let me tell you this. When I take a sample, the result that I got from the sample is what we call sample statistic. I'm going to say that again. The result that we got from the sample is what we call the sample statistic. And at the end of the day, you know what we want to do? We're actually going to use the sample statistic to represent the population parameter. That is what we're going to do at the end of the day. I want to tell you that we've already justified why we need to take sample instead of study the entire population, apart from cost and whether it's going to be time consuming. I'm going to give you this example right now. If a doctor is trying to run a test on a patient, does the doctor need to extract all the blood in the body stream of the patient? That would be suicidal. So doctor is only going to take a sample of blood. So whatever he got from the sample of blood is what we call sample statistic. And he's going to use that knowledge to generalize on the entire population. And I'm going to give you a domestic example before I move on. Maybe my wife is cooking and maybe I'm perceiving aroma from the soup. Oh, what is going on here? Okay, do I need to eat everything in the pot before I know whether it's going to taste great? No. It's just going to dish a part, and I'm going to taste that, and I'm going to have a conclusion about what every other thing is going to be. Okay, now you understand what we mean by that. Now, let me tell you this. I want to explain sampling distribution now. What does that mean? I want to tell you this. If you want to know the average household income in the United States or any country, or I want to figure out the average of certain characteristics of interest, do you know that if two researchers independently, if they conduct study, they're going to have different results? 500 researchers will have different results. 1,000 researchers, it means 500 researchers will have 500 values of means. If I'm not talking about me this time around, if I'm talking about proportion, just like the popularity, the survey that was conducted by MSBC, if a different organization should conduct that survey, they're actually going to have different values. Now, we have more than one mean. It is not surprising that they have different value because they are not using the same participants. They were selecting at random. And you know what? 500 researchers will have 500 means. Then the probability distribution of the 500 means is what we call the sampling distribution. I'm going to say that again. The probability distribution of means, because means now become a random variable. Mean varies. That is what we mean. Several averages. Then the probability distribution is just like, okay, you know what? We want to know, that will give us opportunity to know the range of values. And not only that, with their frequency of occurrence. The frequency of occurrence is actually what I call the probability. Therefore, the probability distribution of the sample means or sample proportions is actually sampling distribution for a given size. Okay, now I want to go into central limit theorem now. You know, when you want to carry out a study from a certain population, you first need to know the distribution. What is the probability distribution of the population from which you actually want to take your sample size? We have a way to do that. We have a way to investigate that. We can actually get the histogram of the population to know. Let me tell you this. The population may be normal or not. I'm going to say that again. The population from which the sample is to be chosen may be normal or not. We don't care about that. But you know what? Situation where we take a large sample size, a sufficiently large sample size. How large is a large? It has to be at least 30. When the sample size is at least 30, then you know what? The sampling distribution of sample means or sample proportion will be normal. I'm going to say that again. Even though the population from which the sample is going to be taken is not normal, provided we choose a very sufficiently large sample. And how large is the largest? At least 30. Then the sampling distribution of the sample mean will actually be normal. And you know what? Situation where it is normal, then number one, you know what is going to happen? 500 researchers have 500 means. Then what are we going to do? We're going to find the mean of the means. I'm going to say that again. We're going to find the average of the averages, because averages become random variable because we have a lot of them. So finding the average of the average will give us the true mean. That is what we're talking about here. That is the mean of the sample distribution of means is now going to be equal to the population mean. That is exactly what we mean. Number two, the standard deviation. You know, we have looked at the averages of the averages, right? The mean of the means. Then we also need to look at the how far apart is the mean of the means from the means. I'm going to say that again. How far apart on average is the mean of the means from the respective means. And that is going to call the standard deviation of sample means. The standard deviation of sample means is what we call the standard error. There's a difference between standard deviation and the standard error. I'm going to say that again. The standard deviation applies to random variable X. But the standard error applies to random variable sample means. And you know what? The standard deviation of the sample mean equal to sigma over square root of n. But let me tell you this, if you want to compare, which one has a lower standard deviation between a random variable X and a sample mean? Of course, it is the sample mean. Because we're divided by the square root of n, sample size, the only condition under which the two of them, they're going to be the same is when the sample size is equal to 1. And it doesn't make sense. When we want to investigate, we don't investigate one person. Do we investigate one person? No way. We have to investigate more than one person. And when sample size equal to 1, of course, the standard deviation of the sample mean will always be less than the standard deviation of the random variable X. And that is giving power now to mean. And that's where we reckon with mean. We reckon with average. Okay, so take a look at that. And you know what? We actually want to talk about the shape now. of the distribution of sample means, even if the sample means that we computed, we actually got that from a population that is not normal, we don't need to worry about that. But provided we choose a sufficiently large sample, and how large is a large? It's has to be at least story, then the sampling distribution, okay, of the sample means will always be normal, will be actually be normal. That's what I'm trying to say. And that was why I said, regardless of the shape of the distribution, we know the sampling distribution of the sample means we approach that of a normal distribution. And the larger the sample size, the better the normal distribution or approximation will be. And that is the reason why we're encouraging us, when you are conducting research, you take a sample size. When you listen to radio or TV and they conducted a study, don't be anxious about the results. Be more anxious about the sample size. Some of them actually use a small sample size. Okay, be anxious about the sample size. It has to be sufficiently large before we could actually rely on whatever they are passing across. Okay, I just talked about population parameters. I just want to show you the notation of what the population parameter is going to be. The population parameter can be mu, can be sigma squared, or proportions. Okay, that is what we always want to know about. But you know what? Because we don't study the entire population, we take a sample, then we're actually going to estimate. So instead of us to get a population mean, we end up getting the sample mean. Instead of going to get the population standard deviation, we end up getting the sample standard deviation. Instead of us to get the population variance, we end up getting the sample variance. Instead of us to compute the population proportion, we end up getting the sample proportion. And you know what? At the end of the day, we're actually going to use the sample statistic to estimate or to represent the population parameter. That's what we do all the time. I want to give you this an example right now on the sampling distribution. I have these 4 guys. They visited me in my office. Of course, the population is 4, but you know what? I only have 2 seats available. I'm going to say that again. I got 4 people. They came at the same time to my office, but I only have 2 seats. Now, in that situation, the population size is actually 4, as you can see here. And you know what? The variable now is actually going to be from 1, 2, 3 to 4. But you know what? The probability that any of them is going to sit is going to be equal. That's a uniform. You remember we did uniform on Monday? Because the uniform is actually going to tell you, the event is equally likely, which means the population of the the distribution of the population is not normal in this case, it's uniform. Look at that. That is what the histogram is going to show you, because they are 4 in number. The probability of any of them is going to say it's going to be 1/4 each. 1/4, 1/4. That will be 0.25, right? That's what we plotted here. But this is not normal. And that's what I'm trying to tell you the other time. The population, the probability distribution of the population that we want to choose from, because I want to choose from 4. I only have 2 seats. It is obvious. It is 2 people that will sit. But the population is not normal. Then what am I going to do? Okay, what I'm going to do, I'm now going to, employ what I call a sampling technique. Do I want to sample with replacements, or do I want to sample without replacements? What I want to walk you through now. I want to sample with replacements, If I want to sample with replacement, what is the possible numbers of samples I can actually take? Or let me just say, what is the possible numbers of ways that I'm going to go into the population? We call that repetitions, like visiting the population a good number of times. The population has 4, but I want to choose 2. Okay, if I want to use something with replacement, the formula is actually going to be an uppercase n raised to power a lowercase n. The uppercase n here is 4. The lowercase n is 2. 4 raised to power 2 will be 16. Then that's why I'm going to have this 16. But you know, take a look at this now. It means if I number them 1, 2, 3, 4, the first one is trying to tell you I choose number 1 person first. I replace that person back into the population. Because I'm choosing at random, there's possibility that I'm going to choose him again. That is why you see 1, 1. So 1, 2, 1, 3, up to 4, 4. These are the possible numbers of 2s that I can actually choose from 4 if I'm sampling with replacements. You know what this look like? This is looking like 16 investigators. 16 investigators that are working independently. They want to choose 2 out of 4. This is a possibility. There are some of the investigators that will have the same results. There are some of the investigators that will not have the same results. Now, if I want to find the mean now, I'm going to be saying 1 plus 1 divided by 2. 1 plus 2 divided by 2. It means I'm actually going to have 16 averages. Those are averages. When I have 16 averages, then I need to look at the probability distribution of that. The probability distribution of these averages is the sampling distribution of means. I'm going to say that again. The probability distribution of those averages is actually the sampling distribution of mean. In a real life practical situation, what do I mean by that? The probability distribution of that will tell us what is the possible values of the mean. The possible values of the mean here is from 1 to 4.0. And what is the frequency of occurrence? That is the probability. When you take a look at this guy now, you're actually going to construct a table. In that table, you're going to write X bar. You're going to write 1.0, 1.5, 2, 2.5, 3, 3.5, 4. Then you're going to create another column. In that column, you're going to write the probability of X bar. What is the probability of X bar? How many times does 1 occur? That will be 1 over 16. How many times does 1.5 occur? 2 over 16. How many times does 2.0 occur? 3 over 16. How many times does 2.5 occur? 4 over 16. Then I'm going to continue doing that. You know what I've constructed? I've constructed, I have X bar and I have their corresponding probability. Then I can plot. When I plot, oh my God, this is what I got when I plot. This is a normal shape. Look at that. Initially, the population, the probability distribution of the population was not normal distribution, was uniform. But after the sampling distribution efforts, what do we have? We have a normal distribution. Okay, but let me tell you this. When you have a normal distribution, we said that the mean of the sampling distribution of mean would be equal to the population mean. If you want to find out what is the mean of the population, that will be 1 plus 2 plus 3 plus 4 divided by 4. I'm going to say that again. The mean of the population is 1 plus 2 plus 3 plus 4, because I have 4 individuals, divided by 4. That will be 2.5, right? If you find the mean of this, if you add everything here together and you divide by 16, you're still going to get 2.5. And that's exactly what I'm trying to say here. Even though the two distributions are not the same, one is uniform, the other one is normal, but you're going to have the same mean. You can verify that.
I have a quick question.
Okay, go ahead.
What does X represent on the table on the last slide? Is it how many people you're choosing, or is it like
okay. You mean what does X represent? Are you talking about
on the left column and then the right, like the top row of the I guess what is 1, 2, 3, 4?
That's a very good question. You know, somebody online is asking about what does 1, 2, 3, 4 represent. You know what? That's just a numbering. You're like giving number to 4 individuals that came to my office. So you are number 1, you are number 2, you are number 3, and you are number 4. Does that make sense?
Yeah, but then, so is the table just the pairs that you're choosing then? Like,
yeah, we want to choose. Okay. Do you know why we want to choose 2? Because I only have 2 seats in my office. I want to choose 2 out of them that would sit on those 2 tables. And that is, that is actually reflecting what happened in reality, where we have a population, but we don't choose all of them. We choose a sample. Does that make sense?
Yeah, that makes sense.
Okay. Now, I just demonstrated to everyone now that they're going to have the same mean. But let me tell you this. They will never have the same variance. The variance of the sample means will be less than the variance of the population, because I showed you the other time when we're comparing the standard deviation. If you want to try that, you can try that. You know what you're going to try? What is the standard deviation of 1, 2, 3, 4? You get the results. What is the standard deviation of the sample of this means? The standard deviation of this means is what we call the standard error. It will be smaller than the standard deviation of the original scores. It has been mathematically proved and statistically observed, because sigma divided by square root of n will always be less than sigma. I'm going to say that again. Sigma, which is standard deviation, divided by the square root of sample size, will always be less than just standard deviation. The only condition under they're going to be equal is when the sample size is equal to 1. No researcher will investigate one person. At least you're going to investigate more than one person. And that is the reason. Okay. Now, I want to walk you through an example now. Okay. This one is talking about the calculating standard deviation for a sampling distribution of sample mean using the central limit theorem. Suppose that the standard deviation of movie ticket prices in the United States is 72 cents. And suppose sample means are calculated for samples of size 52. That is, ticket prices are recorded for different samples of 52 theaters. 52 theaters. Okay, and the sample means are calculated. What would be the standard deviation of the sampling distribution of the sample means? When I say standard deviation of the sampling distribution of sample means, then I mean standard error. That's what we call standard error. Of course, the formula is going to be standard deviation divided by the square root of the sample size all the time for mean. All what you just need to do, you plug in the value of the standard deviation and that of the sample size. Here we're talking about 52 theaters. And at the end of the day, what is the sampling? What is the standard error now? 0.1. And the conclusion is going to be the sampling distribution standard deviation will be that. The sampling distribution standard deviation is actually the standard error. Okay, I want to walk you through another example now. The following histogram represents the population distribution of the weight of 600 Earth Joe kids. The mean of the population is 116.2 pounds, and the standard deviation is 3.9 pounds. You know, if you take a look at this histogram, this will give you the sense that the probability distribution of the population is not normal because this is skewed to the right. Okay, but you know what? They say, let's now consider sampling distribution of the sample means for sample of size n equal to 45. Okay, and they said, can the central limit theorem be applied to this sampling distribution? If so, explain and how the conditions are met. Then B, what is the sampling distribution? Okay, or means, and what is the sampling distribution, standard deviation, and what is the sampling distribution shape? Okay, you're actually going to say that the question actually is centered on the sampling distribution, right? Now, if you want to answer the first question, if you want to see whether the central limit theorem applies, of course, what is the requirement of the central limit theorem? It said, provided, even if the population even if the probability distribution of the population from which the sample size is to be taken is not normal, provided you choose a sufficiently large sample. And how large is a large? At least story, but in this case, the sample size is 45. Because 45 is greater than 30, then the central limit theorem is actually going to be applied. It's applicable. Okay, if the central limit if the central limit theorem is applies, then the mean of the sampling distribution of the mean will be equal to the population mean. In this question, you have been given the population mean to be 116.2. That would be equal to the mean of the sampling distribution of means, because the central limit theorem applies. Now, if you want to get the standard deviation of the sampling means, you calculate the standard error, which is the sigma over square root of n. Of course, the standard deviation given was 3.9. The sample size was 45. You compute that, and that will give you 0.58. On the last question said, you should decide on the shape of the sampling distribution of sample means. And because the sample size is at least 30, in this case, you have 45, and that is actually greater than 30, which is a special requirement for applying central limit theorem. Then we're going to say the sampling distribution of the sample mean will be approximately normal, even though the original population distribution is not normal. And if you want to follow what we did before, if you really want to see that, you go into the population several times and you're choosing 45. You're choosing a sample of 45, and in each occasion, you calculate the means. Okay, you're going to have several means. If you get the histogram of the several means, oh my God, this is what you're going to have. It is now normal. Initially, it was skewed. Look at that. Okay, I want to go into another example now. The following graph displays the starting salaries for law school graduates entering the workforce in 2007. Merely looking at this graph, this is not normal. In fact, this is having two modes. This is bimodal. Okay, take a look at this. It's me, the picture, the histogram of the population will tell you the sense of the shape of that population. Okay. Of course, we got this data set from the Association for Legal Career Professionals. In case you actually want to get more information, you can visit that. Now, what was the question? The question now is describe the shape of this distribution. What is the shape? The distribution that we show. Consider the sampling distribution of the sample mean, okay, of size 25. Can you apply the central limit theorem? When the sample size go to size 50, can you apply the central limit theorem? And when the sample size go to 200, can you apply the central limit theorem? Then starting with the first one, I told you that shape is bimodal, okay? And when the shape of a distribution is bimodal, then you have to look beyond normal distribution, okay? You have to use a particular method that will be robust, okay, to that. Now, when you are given a sample size of, in question B, sample size of 25. For sample size of 25, the central limit theorem does not apply because that is less than the requirement of the central limit theorem. The requirement is that it should be at least 30. But this is 25, and this is less than 30. Because of that, the conclusion is going to be the population that are not going to be normally distributed. Okay, of course, when the sample size is 50, that actually met the threshold. Okay, so the central limit theorem can be applied because we have a sufficiently large sample. And of course, when the sample size is 200, of course, we expect that the population distribution, the sampling, the distribution of the sampling mean we actually approach normality. And let me tell you this, if you increase your sample size, then the variance of that will be decreasing. But the more sample you take, the more we are very close to the truth. Before I go, I want to tell you this. We find ourselves in a world where there can be misinformation, there can be disinformation. If you listen to, if somebody tell you something, if you hear something, don't act very fast. Digest what you heard. Think about it. Or let the person provide an evidence. We don't want to live in a world of, I don't believe in the principle of authoritarianism. I can't just believe I can't just believe what you tell me without verifying. We shouldn't rush to take a decision because what I just walk you through today, if different researchers should go into, if they should actually conduct the same research on the same topic, and even if they are taking the same sample size, but because they are choosing randomly, they're not likely to use the same participants, they're actually going to get different results. But how are we going to harmonize the situation? Then by using the sampling distribution. And that is the reason, if a particular TV station make a forecast, maybe they conduct opinion poll, and they say, this is what we got, I will not rely on that until probably I see 3 or more stations. Then you know what I'm going to do? That will give me opportunity to have different, different values. Then I'm going to do the sampling distribution of that. The average of the averages will be very close to the true mean. So this is reflecting what happened in reality. And that is the reason why you are actually studying statistics, just to be able to know there's going to be, there can be variation from sample, from sample to sample, or when you go into the population several times, even the same investigator, when I go into the population, I choose 50 randomly, I find the mean, I go into that population again, I choose 50 randomly, I find the mean, the value I'm going to get will not be the same, even if I'm taking the same sample size. But you know what? The essence of what we're doing now, sampling distribution, actually provides simplification to the root of taking statistical inference. What do I mean by statistical inference? Making a judgment about a whole based on the field, that is, making a judgment about the overall population based on the knowledge of the field. Because what we normally do all the time, we take a sample, we generalize the results on the entire population. For that generalization to be valid, we need sampling distribution. That is the end of the lecture today. Make sure you stay safe and have a good day.
Thank you. Have
You're
a nice day.
welcome. And you too.
I have a couple questions.
Okay, go ahead.
So with example 8.2 and 8.3, are we only looking at specifically one sample, I guess? I'm trying to get the right term. One sample statistic, because with 8.2, it's just one person's choosing of 600 horse jockeys, but then we just say to apply, we apply it 45 times for 8.2. Is that what it is trying to be said, or is it still, are we have multiple sample statistics?
Okay, if you are talking about the example that I use on the sample size of 45, give me one question, give me 1 minute, 1 second, I'm going to, now, if I'm basically talking about, can you see what I just shared now, right?
Yeah.
Okay. If I'm talking about this one, this guy here, and you know, initially, the population, or let me see, I think it's the other one. Okay, I want to believe that maybe this is the one you are actually, okay. If you take a look at this guy, the population is skewed. Here we use 600 horse jockeys. Look at that.
Okay.
And they have a mean of this and the standard deviation of that. But the population is not normal. It's skewed to the right. Now, what we have done here, we want to go into the population several times and take a sample size of 45.
Oh.
We want to choose that 45 from 600. You get what I mean?
Okay, that
So
makes.
we're gonna go so many times. So on each occasion, you find the mean based on the 45. Okay, if you go 3 times, how many means are you going to get? You're going to get 3 means. But on each occasion, your sample size is 45. Does that make sense?
Yes. So
now,
then,
okay, go ahead.
Okay. And then I guess a follow-up question to that. You said that you would be getting the sample size of you're getting the mean of multiple means. So like, for example, I don't know if you said this earlier, but did you say something along the lines of like, okay, what if we have multiple, like, let's say, right, there is multiple people who sampled 600 horse jockeys and it might be different means and different standard deviations, then what would you do something different for that, or was that, or I got confused?
No, actually what I said is this. What I said is that you're going into the population several times. You are choosing 45. And don't forget, the population you are choosing from is actually 600. There are several ways to choose 45 out of 600. Do you know that if you are using the sampling with replacements, the possible numbers of ways of doing that is going to be 600 raised to power 45? You know that?
Yeah.
If you follow the example that I showed the other time where 4 people visited my office, and of course, you know, I want to choose 2 people because 2 seats are available. what and I was sampling with replacement, that was, and, that would be 4 raised to power 2, which means we have 16. But in the case of this one now, we're going to have a lot because it's going to be 600 raised to power 45. Now, that would be the numbers of means you were actually going to get. But in each occasion, you are taking a sample size of 45. When you take a sample size of 45, you're finding mean of each of that.
Okay.
Now, when you now find the mean of each of that, take a look at this. That is what we are plotting here. We have a lot of means, sample means here that you are actually plotting. When you take a look at this shape now, it's approximately normal. And this is what I'm actually talking about, that where the population distribution is not normal, then this when we actually, do sampling distribution of sample mean, provided the sample size is at least 30. In this case, the sample size is 45. Therefore, the sampling distribution of the sample mean will actually be normal. Do you understand that now?
Yeah.
Okay.
I have 2 more questions, but I don't know if anyone has more. I don't want to.
Yeah, I think you are the one. Let me just see. At this time, I think it's only one person left apart from you. I think you are 2 now.
Okay.
So go ahead.
So, and then I guess, so this is unrelated to today's lecture, but I was looking back at the different, what was I was looking back at the other lectures, and then you did like a computation that I was confused on. It was like, you did combination like 6, 2, 1, 3, and I forgot how do you compute combination when it has more than 2 values? What does that imply?
Oh, you mean that is that is not from today's lecture, right?
No, it was from a previous one.
Oh, okay. You know what I will advise that you do? Can you visit with me during the office hour tomorrow? Then I will be able to answer anything that has to do with other lectures. If your question is going to be based on this one, I'm ready. But if it is not, then I can actually listen to you when you visit during my office hour tomorrow.
I was just trying to I understood the lecture overall is just how.
Yeah. This fall in the middle of lecture because I also have some other, I'm so sorry about that. I have some other activity so in fact, the class I'm using now, where I am now, some other student, they're going to have a class. You get what I mean, right?
Okay.
So, and that is the reason why you can actually visit me during my office hour if you want to ask questions about other lectures. Does that make sense?
Okay. Okay. And then another question is, are you going to provide a practice exam for midterm 2?
Exactly. I would definitely do that. In fact, I'm actually going to walk you guys through the midterm 2, just like what I did for the, midterm 1. Does that make sense?
Yeah. And then one final question. I have a trip so there's a conference in New York and they're asking for a teacher recommendation. And I was asking if it's possible if I could put you down as a contact for that.
Yeah, that's no problem.
Okay. I just want to make sure before I put it down.
That is no problem at all. You get what I mean, right? That's no problem.
That's all I have to ask. I guess I'll see you at office hours tomorrow. Then.
Okay. So make sure you stay safe, okay?
All right. Thank you so much.
You're welcome. Yeah, bye.